This video is for section 7.2, measuring the quality of a survey. Specifically, we're going to be looking at accuracy and precision. So oftentimes, statisticians evaluate the method used for a survey, not the actual outcome of the survey. So here's an example to show why. If a group of researchers were to survey 1,000 randomly selected people, we would expect the results to vary from sample to sample. Because we would want to know how the group did as a whole, we would evaluate the estimation methods, not the individual estimations, because of that variation. The goal here is to be both accurate and precise. Accurate means that the method measures what it intended to, and it also correctly estimates the population parameter. Precise means that if the method is repeated over and over, the estimates are likely to be very consistent. So here is an example to demonstrate accuracy and precision. If the goal in golf is to get the golf ball in the hole, which of these pictures shows a method that is both accurate and precise? So let's take a look at the first picture at the bottom left. In this picture, you see that all of the balls have been centered or hit that makes it centered around the hole. And in fact, some of them have landed in the hole. This is an example of accuracy and precision. The second picture in the middle shows golf balls that are tightly clustered together. So it's very precise, but it's not accurate because they aren't centered around the hole, which is why none of them made it in. And on the third picture, you can see that all of the golf balls are centered around the hole, but it's not very precise, again, which is why none of them made it in. And this is a good example because we want to think about our experiments as taking now many samples. And remember, when we measure these many samples, we want to try to do it in a way that is both accurate and precise so that we can make an inference on the population, right? So think of the whole, our target here, as the population. Like we're trying to hit, right? This target. And we have many different samples that we're taking, many samples. So each golf ball here would represent a different sample. Each time you take a sample, you're not necessarily going to hit a measurement that is exactly the same as your population, but you want to do your best. So you want to make sure it's accurate and precise every sample so that you can make the best inference possible. Okay, so to understand the behavior of estimators, here's simulation 1. We have a small population of 8 people, 2 of whom are cat people and 6 of whom are dog people. Random samples of 4 are taken from this population, and the percentage of cat people are noted for each sample. Note 25% of the population are cat people. So the question is, will each sample contain 25% cat people? And is it possible to get a sample with 0 cat people? Right? So think about the golf balls. Every time you hit a golf ball, are you going to hit your target? So before we proceed, one more thing where it says note that 25% of the population are cat people. Let's identify this 25% like we did in section 7.1. So question here I'm asking is 25% P the parameter or P hat a statistic? Well, because 25% is coming from the population, we know that this is a parameter. Okay, so here's the results from 3 random samples, right? So 3 random samples, sample size is 4, which is why you see 4 in each sample. So the first sample taken, there is 0 cat people of the 4. Second sample, 25% cat people of the 4. And the third sample, there is 25% cat people of the 4. So here's those same results, but displayed in a table. So note that the sample proportion, p hat, changes from sample to sample, but the population, sample p, remains the same. So remember, we're not changing anything about the population, so that parameter is not going to change no matter how many samples we take. But each sample is going to vary a little, just like how the golf balls did. Even when we're accurate and precise, not all the golf balls went in. So each sample is going to have a little bit of variation, but we're hoping that we hit the target of 25%. Okay, so this is what the sampling distribution of p hat looks like. The probability distribution of p hat is called the sampling distribution. We can represent it using a table or a graph. So notice now we're talking about probabilities, and we're pulling in stuff that you guys learned in chapter 5 to go along with our sampling estimates. So on the left, you just see the table with the probabilities, and on the right, this is how a graph of that sample proportion would look like. Okay, so here's some notes about the simulation. Our estimator, p hat, it's not always going to stay the same, right? But our parameter p will, because that comes from the population. The mean of the sampling distribution is 25%. So it ended up being the same value as p, which is our target. And this is an indication that the estimator, p hat, is unbiased. So the estimator, right, our sample, how we did everything, that's an indication that it was accurate. And even though p hat is not always equal to p, the estimate is never more than 25% points away from p. When we talk about precision, now we're talking about standard error. Standard error is the standard deviation of the sampling distribution. So it's kind of like, well, it is the standard deviation of all the sample means. It measures how much an estimator typically varies from sample to sample. When a standard error is small, we say the estimator is precise. So the standard error tells us how far off we might be from our target from sample to sample. So standard error has a formula that we're going to use to calculate to see exactly how far off we could be. Notice in this formula we're using population parameters for p, and n would represent the sample size. But we know that we might most times actually not have the population parameter because that's what we're trying to find out, right? We're trying to make measurements for that population. So most times we don't have that. So the formula that we'd actually be using is an estimate of the standard error. And this estimate uses p hat, which comes from the sample. All right, so here is simulation 2. We're going to use a larger population. This time our population is 1,000 compared to the first simulation, it was 8, right? So of these 1,000, 250 are cat people, which still makes our population parameter 25%. So we're going to take random samples of size 10 now, and find the sample proportion, p hat, of cat people in each sample. Using technology, 10,000 samples were taken, and the results are shown in the graph on the next slide. So before, remember, we only did 3 samples of 4, size 4, but now we're doing 10,000 samples. So we're running this simulation 10,000 times. So here is what the graph looks like based on our larger population. Notice this red dot or red triangle at the bottom on the horizontal axis. That represents the mean of all of these means. So this is what we call a sampling distribution, which means these are all means, the means of all the 10,000 samples. So think of it as if we did 10,000 samples, and each time we did a sample, we found the mean. And now we graphed each of those numbers, and that's what is a sampling distribution. Okay, so it looks like in this slide, my p hat has moved. This is supposed to be p hat here. All right, so looking at the data, since the center of the distribution is about 25%, notice that's where the red triangle was, so it was still 25%. Of the bias, p hat is still 0, so there's 0 bias, even though a larger population and sample size were used. The variation of p hat is less. This estimator is more precise, even though the population is larger. In general, the precision has nothing to do with the size of the population, but only with the size of the sample. So what we're saying here is that when we increase population and sample size, it's not, our bias is still going to be 0, right? The variation is what we're focusing here on this example, is that the variation, in other words, standard error, will be less because we're increasing the sample size. Okay, so to make more of a point here, simulation 3, large samples produce more precise estimators, what we kind of just talked about, right? So again, we consider population of 1,000 people, and we still have P at 25%, but this time we're increasing the sample size. It's not 10, it's now 100. And we're doing this 10,000 times. Compute the proportion of cat people in each of the samples. The following slide shows the results of this simulation. So you guys see the difference here, right, from the previous simulation. We're keeping the exact same population, same parameter. The only difference is now we're increasing the sample size. From the last time, we increased the population size and we didn't see much change there, but now we're increasing sample size. And this is what's going to happen when we do increase the sample size. Notice where the red triangle is, still mean of 25, but now look at the variation in the graph. The variation is more tightly clustered towards that goal, right, the target of 25%, showing that we have more precision and less standard error. Okay, so here's some notes about what happens when we increase the sample size. The estimation method remains unbiased, right? The center is still at 25%, which is where that red triangle is. But the shape of the histogram is more symmetric than the one for a sample size of 10. The estimator is more precise because it uses a larger sample size. Standard error is smaller. So the point here is that sample size, remember we talked about the gold standards. There are 4 of them from chapter 1. Large sample size was one of them. And that's why it's so important, because we want to decrease the standard error. Okay, so summary of the 3 simulations. The estimator, p hat, is unbiased for all sample sizes as long as we take random samples. Okay, so to avoid bias, you want to make sure that you're doing a random assignment. Again, that was also one of the 4 gold standards, random assignment. The precision improves as the sample size gets larger. So we want a large sample size as well. When we do that, the shape of the sampling distribution gets more symmetric because there's less variation. So the point is, increasing sample size improves precision. Also, you should add here that random assignment reduces bias. So here's the last example. According to Mars Company, packages of M&Ms contain 20% orange candies. Suppose we examine 100 random candies. What value should we expect for our sample of orange candies? And what is the standard error? So let's go ahead and identify all the parts here. So first of all, what is the population? Well, according to Mars Company, packages of M&Ms contain 20% orange candy. So we don't know what the population size here is, but we'll say that the population is all the M&Ms. And we also see that we're examining 100 random candies. So that is our sample size. Now we have this other number here, this 20%, right? And here's where we're going to determine, is this P or P hat? Well, because it's coming from all the packages of M&Ms, this tells us that 20% is P. So the first question is asking, what value should we expect for our sample of orange candies? In other words, what should we expect for P hat from our sample? Okay, so remember, we want to try to hit the target every time. We expect to hit the target every time, and because we see that it has, the sample has been taken randomly, random assignment, that tells us there was no bias. Because there's no bias, we can expect to hit the target of 20% for our sample. Okay, so now we know it's not biased, so we know it's accurate. Now let's go ahead and calculate precision by finding the standard error. So here is the standard error formula. And remember, oftentimes we don't have P, we most likely have P hat, but in this case we do have P, so we're going to be replacing P with 0.20 and N with our sample size of 100. Okay, so I went ahead and replaced the P's with 0.20 and the N with 100. But what I'd like to do here is I want to explain this numerator portion up at the top. This is when we talked about in chapter 5 complements. Remember, if the chance of rain is 20%, what's the chance of no rain? Well, that's going to be 80%. And that's what we're working with in this numerator up here. It's always going to be complements. So to make it easier when you include this in your calculator or however you're going to calculate it, I would just write the complements for that 1 minus p part. So right off the bat, when I put in the 0.20, I know that 1 minus 0.20 is going to be 80%. You see, those are always going to be complements in the numerator. It makes it easy for us to calculate standard error. So when we calculate the standard error, it comes out to 0.04. Now we can go ahead and answer the question or fill in the blank to answer the question. So we expect 20% orange candies, right? Because we expect to hit our target. Give or take. Give or take means what is the error that we may or may not have? And that is going to be, as a percent, 4%, right? Because previously we had a decimal, but if we change it to percent, it's asking for us to write it as a percent. It's give or take 4%. So if we repeat this sample over and over and over again, we expect to be at 20% orange candies every single time. Do we get it? No, we may be off, give or take 4%.